In this problem, we have a beam undergoing a distributed load, and we want to find the reactions at the pin at C and the tension in the rope that will keep the system in static equilibrium. So we want to find reactions at C, and the tension in the rope I will call T, and that rope is going over a pulley. We can make the free body diagram of our system. In this case, the system I'm going to isolate, or the object I'm going to isolate, is the blue bar CAB. So I'm going to isolate it from the pin, and I'm going to remove the rope itself and see how that is impacting what remains. I have a bar that goes from C to A to B. And I want to put all the forces, all the moments that are acting on this bar. So I have the reactions at C, I have the tension going from A around the pulley to B. I'll start there since we've seen that before. So one way I can model this is I can keep just a little bit of the rope just to remind us where these forces are coming from and where their directions are coming from. So I can see the tension in the rope here I will call T. And because it's one continuous rope from A around the pulley to B, I know that the tension is constant when we're in a static situation and we're ignoring or there's negligible friction at the pulley, that same amount of tension T will be at the rope on the other side. And that's going at this 30-degree angle. 15 feet and 15 feet. And I'll put the reaction at C now because we know what that looks like from earlier, is a horizontal component and a vertical component. I will assume positive right and positive up. Now we can address the new part, this distributed loading that's happening. So we have a loading that goes from C to A that is uniform or rectangular over a 15-foot span. Its intensity over that whole span is 800 pounds per foot. And then from A to B, it's linearly decreasing from A to B, starting at intensity of 800 pounds per foot, going down to 0. And we can also call that a triangularly distributed load. So what I want to do in my free body diagram, this external free body diagram, is simplify the distributed load to a point load, or in this case, I'll actually do it as 2 point loads. It's rectangular from C to A and then triangular from A to B. I could treat this as a trapezoid if I wanted to, but typically I'm going to find it easier if I just split it into 2 shapes and then have 2 point loads. So I'm going to look at the rectangular load first and simplify that. And then kind of separate from that, I will do the triangular load then. So this in green, the rectangular loading that goes from C to A, I want to know what's the equivalent force and where should I put the point load so that it is going to create the equivalent moment. So to do this, the force is going to be the area under the distribution, and the location where I put the point load is going to be at the centroid of this shape. Right, so let's start with where am I going to put it? Where's the centroid? It's a rectangularly distributed load. I only care about the horizontal position here. It's going to be, since it's a rectangle, at half of its distance. So it's going to be acting here at 7.5 feet from C, which is also 7.5 feet from A. And I'll mark that A, and I mark this B. Okay, so that's where it's acting, again, at the centroid, at least the horizontal centroid of this shape, of this rectangle. And now with what force is it acting? So I want to look at this again as a rectangle. It is 15 feet long, and the rectangle has a height of 800 pounds per foot. We can think of it like that. So the area is going to be 15 feet times 800 pounds per foot. So the feet are going to cancel and I will be left with pounds. So the equivalent loading is going to be 12,000 pounds. That's just from the rectangular part of this distributed load. So I know where I'm putting the point load and the value of it. So I've simplified the rectangular load into this equivalent point load. And now it looks like something we've been analyzing with 2D rigid body problems. Now I can go on and look at the triangular part of the load. And again, I'm going to do that kind of as its own calculation instead of trying to put both point loads into one. So I have here a right triangle that has a base of 15 feet, and I can say that its height is 800 pounds per foot. So first, let's see, where should the equivalent point load be located? It's a right triangular load, so in a right triangle, the centroid, we're only going to look at the horizontal for here. The horizontal centroid is located 1/3 of its base from the right angle. So if the whole thing is 15 feet, then it is located 5 feet from the right angle, or 10 feet from the point B. So I'll put both of those dimensions in here. I'll put those in the regular font. So 10 feet from B, 5 feet from A. Okay, so that's its location, and now I need the equivalent force. Just like with the rectangle, the equivalent force is the area under my distributed load. So 15 feet times 800 pounds per foot times 1/2 base times height, I'm going to get an equivalent loading of 6,000 pounds. So for the triangular section of the distributed load, I know where it's acting at 5 feet from A or 10 feet from B, and I know its equivalent force is 6,000 pounds. Now I have my complete free body diagram. I've converted the distributed loads into equivalent point loads, so now I can proceed just like any other 2D rigid body problem. And again, externally, what I've done, the simplification, is fine. It will not impact my values that I find for CX, CY, or T. But as a note, in the last section of this course, when we get to internal loading, we want to be careful when we are simplifying these loads. It's fine for the external loading, but when we go into the internal forces, internal moments, we just have to be more cautious when we do this simplification. So now for our equations. I will start here with actually the moment around C, because that way I'm eliminating CX and CY from this equation. So taking the sum of moments around C, I'm going to have, if I go from point C and go to the right, I will encounter this 12,000 pounds clockwise, so minus 12,000 times 7.5 feet. My base units here are pounds and feet. Everything will be in those base units. So negative 12,000 times 7.5, it's negative because it is clockwise around point A. As I keep moving, I have this 15 times T from the tension located at point A. I will have a 6,000 pounds times a distance of 20 from point C, and that is going to be clockwise, so negative, and then plus a distance of 30 times T sine 30, just the vertical component of T that's located at B, and it has a perpendicular distance of 30. All right, so from equation 1, I will be able to solve for T. I'll save that for the solve step, but it is solvable right away if I so choose, but I'll hold off just a minute. Right, now I can go to equation 2. Well, I have force equations left, so I will do those in the meantime. So if I sum forces, this is a sum of moments, let's sum forces in the x direction. And doing so, I will have all of Cx pointing to the right, or at least that's my assumption, minus T cosine 30 degrees. All right, by the time I get to equation 2, I will know the value of T, so I will be able to solve Cx. That will be pretty straightforward. And equation 3, if I sum forces in the y direction, I assume Cy is pointing up, minus 12,000 from the distributed load, the simplified distributed load, plus t is pointing up at point A, minus 6,000 from the triangularly distributed load, plus t sine 30 from the tension acting at B. And we see here in equation 3, I will know t already, so I will be able to find cy easily. So from equation 1, t is my only unknown. I am going to find that it is 7,000 pounds. Positive. I assumed it was tension. It's positive. It is in tension, which it's a rope. It must be in tension. So that's a good quick check there. Using that result in equation 2, I can find Cx is going to be 6,060 pounds. And it's an external force, so I do want to indicate its correct direction. I assumed it was pointing to the right, and that assumption was correct. And equation 3. Cy is the only thing I don't know now that I know t from equation 1. So Cy, I get 7,500 pounds. And again, it's external, so I do want to indicate its proper direction. I get positive 7,500. I assumed positive up in my picture, so indeed it is pointing up. So I got my 2 reaction components at C, and I got the tension in the rope, which is what I was asked to find. And I did it by simplifying the distributed loads. I chose to split it up into a rectangle and a triangle, and then individually find their equivalent force and equivalent location, and then solve the free body diagram from there. Alternatively, I could have treated it as a single trapezoid and then found the equivalent force from its area and its equivalent location from its centroid, but I think that's usually more trouble than it's worth. It took 2 point loads, but it didn't really complicate the problem too much.